Mr. Mohan Kumar?
Am I audible?
Yeah. Yes, sir. You are audible. Mr. Mohan Kumar, please continue.
Hello. Yes, sir. I'll start, sir. Now. Yes.
Yeah,
Yes,
please.
Yes.
Yes. I am audible, right?
Yes, sir. Yes, sir. You're audible, sir. Yes, sir.
Okay.
Yes, sir. Yeah. Okay. So welcome back, everyone. So resource person has joined us. So on behalf of the management of Mangalore Institute of Technology and Engineering and principal and also the Department of Mechanical Engineering, I extend the warm welcome to our resource person, Mr. Durvankur Raut, who is the Chief Engineer in Device Electronics Private Limited. So welcome you, sir.
Thank you very much. So
I also, yes, sir.
Yeah.
I also welcome all the participants to this session 9 of the day 3 of this 5-day FTP. So I would like to present a brief introduction of Mr. Durvankur Raut. Already he is known to all of you because yesterday also he has delivered one session. So briefly I will read out his introduction. So Mr. Durvankur Raut is currently working as Chief Engineer in Device Electronics Private Limited, and he has obtained his BE in Mechanical Engineering from University of Pune and postgraduate diploma in Patent Laws from National Academy of Legal Studies and Research, University, Hyderabad, and his MTech in Solid Mechanics and Design from Indian Institute of Technology, Kanpur. So he is leading the role of managerial, team building, and business-related activities in Device Electronics Private Limited. He has built an electric vehicle integration team in Device Electronics and also leading a team of multidisciplinary engineers working on interdisciplinary projects. He is involved in electric vehicle integration design and manufacturing, electric vehicle battery pack design and manufacturing, and IP-rated enclosures for battery packs, wearable devices, PCBs in general. He is also actively involved in building organizational capability in electric vehicle battery pack design, training in electric vehicle technologies, and leading a team of specialists to deliver training on various technologies on OEMs, Tier 1s, and in-house. So he has conducted electric vehicle training for the various technical leaders and build teams and production teams, electric vehicle professionals, R&D engineers, etc. She has concentrated training on EV battery pack, EV charging infrastructure, and for his great contribution to the field of engineering, he has been awarded and honored with Tech Acharya Award, awarded by Mahindra Technical Academy, MRV Chennai, in February 2020 for excellent contribution to enhance the technical competency of Mahindra's product design engineers in the field of electric vehicle technology. With this brief introduction, I invite Mr. Raut sir to deliver the talk on the topic component sizing and integration. So with this, I hand over the stage to him. So please, sir, please take over and please continue with the presentation. Thank you.
Yes, sir. Just give me a minute so that I can present my screen.
Yes, sir. Yes, sir.
Yeah. Can you all see my screen?
Yes, sir. Yes, sir. It is streaming, sir. It is streaming. Yes, yes, sir. It's visible, sir, now.
Okay. So we will be talking about EV architecture and some calculations for battery and motor sizing. I used to call it range and power calculations because range will finally decide what is the battery pack capacity, and power is something which will decide what is the motor's capacity going to be. So now that you have been through some trainings over the past few days, uh, can you help me building the EV architecture diagram? So what is the most important part in EVs, which you know? What is it that EVs will have? Will there be a battery pack? Yes?
Yes, battery pack.
Okay, let me just draw it again. So there will be one battery pack. What will this battery pack be connected to? It will be connected to something called a junction box or PDU, also known as power distribution unit. And through this junction box, there will be several connections which will come out. And one of them will go to inverter, or also called as MCU, motor controller, or also called as TCU, torque controller unit. And through this inverter, it will go to which component? Inverter to motor. Motor will convert this electrical energy into mechanical energy, and that means it will rotate the shaft. And this rotation of shaft is coupled with a, maybe I can just write all this thing in a block as well. So it will give this rotational energy, mechanical energy to gearbox, or we can also call this transmission. And from transmission, it will go to wheels, right? So this is basic architecture of the vehicle. Now, when you have all these things in it, will the vehicle run based on this? So yesterday we talked about batteries and BMS. Will the battery run without BMS? Can you guys hear me?
Yes, sir. All are hearing, but a little bit shyness they are showing. Please continue, sir.
Okay. So unless there is response from you, I am not moving ahead. You guys
Understood.
need to talk.
Yeah, understood. Please proceed, sir.
So otherwise, what happens is it just becomes monotonous. I'm just talking here. I don't know whether people are understanding it or not.
Yeah, please post questions in between. Let us see whether they're sleeping or awake.
So will the battery work without BMS or not? Battery work without BMS as well.
Yeah,
So,
they can chat also. They can send by in the chat box.
okay.
Right.
I'm not able to see the chat window because if I'm sharing screen, everything goes away in the
Okay.
presentation mode.
Right.
So
Right.
anyway, the BMS is not
It won't, sir.
necessary
It
for,
won't. We need BMS, sir.
yeah, we need BMS not for operating the batteries, but for
Management.
making sure that the batteries remain in their safe operating area, right? You remember what we talked about yesterday, SOS, safe operating area. Although BMS we covered in very haste in like the last 10-15 minutes, but the important thing to understand here is BMS is just a controller which is operating some switches here after the battery pack or within the battery pack, and what it just makes sure that the battery remains in its safe operating area from the point of view of voltage. The voltage should not go very high, voltage should not go very low, should not cross the low voltage limit, should not cross the high voltage limit. Same way, the current should not go beyond particular value of highest current allowed at given state of charge limit. Same way, the temperature should not go beyond the specified limit of the temperature for a battery pack, for the cell which is used in the battery pack. So all these things BMS will take care. But the thing is, BMS is not necessary for the battery to operate. We have been using battery packs or cells in like our remote controls, in wristwatches, in wall clocks. So they don't have BMS in them, but the batteries still operate, right? So same way, these batteries also operate without BMS. Just that we won't know if the battery cross its safe operating area, and that's why we need a BMS to control that, to kind of make sure that the batteries don't cross their safe operating area. Now, after this, the energy comes to PDU. PDU, what PDU does is it is just the power distribution in it, as it is called. So it distributes power to multiple things. So first of all, it distributes power. Make sure that the power flow is right. So there will be one charger which will be there. This charger will charge the batteries, and it will also be connected to the batteries through PDU. Now, once the charger is in place, let's say if you want to charge the battery, then what you will do is you will have to switch off the vehicle, put the vehicle on charging, and that means if that is happening, that means the vehicle cannot move. If it is charging, if you are using a charger, that means the charger wire is connected to your vehicle. So at that point, you are not allowed to use the vehicle. Otherwise the wire will come out, right? If the motor runs, and that's why this needs to be cut off. The inverter needs to be cut off from the battery pack, and that is done in the PDU through some controllers again. So we'll just talk about those controllers in a few moments. So the other way around, so when the charger is connected, the inverter won't work, and when the inverter is connected, if vehicle is moving, then it won't go into charging mode. Okay, and that is made sure by the PDU. So this PDU also gives so it kind of distributes high voltage power. Battery pack is a high voltage system, inverter is high voltage system, charger is high voltage system. It also operates some other high voltage systems like HVAC. HVAC in EVs is generally a high voltage system. So HVAC is, do you know what is HVAC?
Heating, ventilation, and air conditioning.
Yeah, so we can just call it air conditioner for like being more closer to us. So air conditioner will also work on high voltage system. And if at all there is a heater, air conditioning both. The heater will also be high voltage and air conditioner will also be HV component. And both these will be again connected to PDU. Okay. I'm drawing two connections here because one of them is HV positive, another is HV negative, right? High voltage positive, high voltage negative cable is coming out of the PDU. Another thing here needs to notice is there will be also some low voltage component which will be connected. So there will be one. So PDU will also have most of the times. Okay, it is not getting erased somehow. It will, most of the times it will also have something called as DC-DC in it, DC-DC converter. So this DC-DC converter will give out 12 volts output most of the times, 12 volts or 24 volts. 12 volts for passenger cars, for two-wheelers, and 24 volts for heavy commercial vehicles. For light commercial vehicles or heavy commercial vehicles, 24 volts battery is there. And this 24 volts or 12 volt battery, in this case, is called as auxiliary battery. What this auxiliary battery does is, now just imagine a case when this battery pack is completely dead. This battery pack is completely dead, and in that case, if you try to start the vehicle, it doesn't move. And if it doesn't move, how will you know that it is what is the problem? Somebody has to be there to kind of diagnose the problem and tell to the user that this battery pack is dead, that's why you're not able to move, that the battery pack is completely empty, it is 0% charged. We won't know that unless there is somebody to tell us. And that system can work only with some amount of power, and that amount of power cannot come from the same battery pack which we want to analyze. So it is like if you are a faculty and if the student is needed to be, so if you want to know whether the student knows, the student has the knowledge of the subject or not, but you are asking the student himself that whether you have the subject knowledge or not. And if the student is not able to answer that because he doesn't know what is happening, so same thing happens here. I may not have put the correct analogy, but I guess you have understood that if the battery packs itself needs to be analyzed whether it is working or not, you cannot rely on the power which is coming from the same battery pack, right? So that's why you need some other battery pack which is generally working with 12 volts or 24 volts. And why 12 volt or 24 volt? Because these controllers like BMS will also be working, will also have power which it will need, either it will be 12 volts or 24 volts. Okay, so same way some other controllers. Let's say if I'm talking about now, let's use a different color for all the controllers. Okay, so this is a BMS here as a controller. Charger will also have charge controller, CCU. Okay, same way on the vehicle side, there will be one charger controller, VCCU. Okay, this is a controller on the charger, this is controller on the vehicle for charging. Same way on the inverter, there will be one controller called motor controller in it, MCU. For air conditioner also, you might have a separate controller for maybe thermal management of the air conditioner and so on. So there might be a separate ECU or the same master ECU. ECU in this case means electronic control unit, a microcontroller based electronic control unit. Now this, so we might have a master one which generally is called VCU, vehicle controller unit. Please pardon my spelling. Vehicle controller unit, VCU, and this VCU will also draw this 12 volt power from the same auxiliary battery pack. The motor controller will also draw the auxiliary, the 12 volt power from the same auxiliary battery pack. The VCCU also is supposed to draw the 12 volt power from. Yes, please go ahead.
Can you use dark color when it is not visible?
Okay. Is this green color visible?
No, sir. No, sir.
This green?
Yes, yes. This is visible. Yes.
Okay. You should have told me earlier. I need to erase everything now. Okay. So there is this BMS, sorry, charge controller CCU, vehicle controller VCU. There is this motor controller MCU, and all of these things are drawing power, 12-volt power from the auxiliary battery pack. Okay. They will also have some communication channel amongst themselves. So there will be communication going on between vehicle controller, between BMS, motor controller, charge controller. So this, okay, let me just try using this blue color. Is blue color visible, sir?
Yes, sir. Yes, sir.
Okay. So there will be a communication between BMS and VCU, motor controller and VCU, charge controller and VCU, and some other sensors and actuators as well. Sensors like there will be accelerator pedal sensor. There will be brake position sensor. Some other sensors like let's say rain sensor, light sensor, and so on. And actuators like your maybe the wiper actuator. So other actuators the same way. So VCU will be driving all these actuators and sensors. It will also communicate with the motor controller, the charge controller, battery management system, and so on. And in this case, now I might be drawing kind of one VCU, but there can be multiple VCUs. Some of them just doing the job of master controller, some of them just doing the job of body control module, and so on. So multiple ECUs are there. Some of the ECUs are just making sure that just made for the seat adjustment and seat heating, and air conditioning might have its own ECU. So all these different ECUs, they generally are connected to one master, which is called as vehicle controller unit. So vehicle controller unit has all the information that what is the accelerator position sensor, accelerator position, what is the accelerator position, what is the brake position, is the rain sensor active or not, is the wiper working or not, like that. So all this information VCU has. What is the SOC level of the battery pack, state of charge of the battery pack, what is the motor controller's input right now, or motor controller, how much current the motor controller is drawing, how much current the air conditioner is drawing, what is the temperature of the cabin. So it might have temperature sensors as well. So all these things the VCU is handling. It is called that's why it is called master controller as well. Now about our today's session, we need to understand how the power is flowing. So to understand the flow of power, let me just change the color to some darker color like black color. So the energy is coming from battery pack towards the inverter most of the times, and towards the air conditioner, towards the motor, towards the transmission, towards the wheel, right? If at all the vehicle is into regeneration mode, in the regeneration mode, energy will come from wheel to transmission, from transmission to motor. Motor will work as a generator or alternator. Give it to inverter. Inverter will work as rectifier. Rectifier will give it to again junction box. Through junction box, it will go to the battery pack as a charging energy. Okay. So the power can flow from battery pack to DC, so from battery pack to PDU to inverter to motor to transmission to wheel, and in reverse way, exactly reverse way during regeneration. So this happens during drive, during the acceleration, and this happens during the regeneration. So regeneration might happen because of the braking, regeneration might happen because of the deceleration. So when you put when you take out the foot over the accelerator pedal, as soon as your accelerator pedal position is sensed at 0, VC will sense it and send that signal to the inverter to work as rectifier. And because the energy will start coming now, because the wheel is rotating the motor, and motor once if motor is not taking any energy, so you must have also gone through maybe yesterday there was one more session by Mr. Shekhar Malani, right, who talked about motors, right, just after my session. So there you must have seen how the motor also runs as generator, and once it starts running a generator, it will give out electrical energy which can be converted into a DC energy and can be given to the battery pack for charging. So this is how power flow in vehicle occurs. When you press accelerator pedal, it is sensed by VCU. VCU will tune the inverter through motor controller. Motor controller will tune the inverter. Tune the inverter for given. So what it will do is it will sense what is the position of the accelerator pedal. It will sense what is the speed of the wheel. Based on the speed of the wheel, it will adjust the frequency of the inverter. Based on the accelerator position, it will adjust the current which needs to pass through the motor, pass towards the motor. And now frequency and current value is known. Based on that, it can derive what is the voltage it needs to apply. So all these things it will do internally, and then you will start that the vehicle is accelerating. Okay. Now, when I'm talking this, it takes about a minute to understand or kind of tell this process. The controller, VCU and MCU together, they need to do this within few milliseconds, right? That's why they need to be very strong. Now, this is how the power flows. Now here, the important components which we need to understand are first of it is battery. Second is motor, which also works as a generator sometimes. Okay. So, and third one is wheel. Okay. So only three components we'll be targeting now. Here, battery pack is storing and returning energy. Which is in electrical form. So although the storing is in chemical form, but we'll just, for the simplicity, we'll call it electrical form of energy. Motor is converting electrical form of energy into mechanical form of energy. Transmission is increasing or reducing the torque based on what is the user input, based on what is the how is the motor designed, based on what is the what does the user want. If the transmission is changeable transmission, shiftable transmission, then it will shift the gears also based on what is the user input again. And this increased or reduced torque is fed to the wheel, and when the wheel rotates, it pushes the ground back so that the wheel can move forward, right? When it pushes the ground back, the ground cannot move because ground is grounded, as in it is a rigid body, kind of practically rigid body, so it cannot move. So it asks the vehicle to move. The wheel needs to move because the ground cannot move. But actually what is happening is wheel is pushing the road backwards, and that's how the vehicle can move forwards, right? Now, to understand how the energy is flowing, what we are saying here is there is electrical energy, there is mechanical energy. So we need to understand that there are some conversions happening here, and these conversions, if we need to understand some fundamental terms here. And while talking about these fundamental terms, we'll also write down their SI units. Okay. Now, what is force?
Newton.
Force SI unit is Newton, but what does it signify? It signifies that this is something which is responsible for change, right? So it can be change in the position, change in the flow of current, change in the maybe state of rest or state of motion. What is range? We know range as distance. And what is the unit of distance? SI unit?
Kilometer, meter.
Speed SI unit?
meter per second.
Right. So I'll be just going little fast because we just have 1 hour. Acceleration SI unit.
Meter per second square.
So generally when I take this session, I take it for 4 hours. So you can imagine we can go into much depth when talking about these terms. But for now, we'll be just making sure that at least SI units are known. Energy
Joules.
or
Watt. Newton.
right, work done
Joule. Newton meter.
or why do these two terms have same units?
Work done is stored as energy.
The stored energy is sometimes used as work which is being done. So if I'm having a vehicle and it moves from this position to this position, that means some work is being done. I need to push this vehicle with some force, then it moves for a distance, let's say yes, and this force into displacement will give me how much work was done. Newton into this meters of distance will give me how much work was done. And to do this work, some energy from the, let's say, battery pack or some energy from fuel in the IC engine, it got utilized, and that energy is in joules. So that's why energy and work done, they are analogous to each other. They are like similar terms. The only difference is when the energy is getting converted into work done, there are some losses, right? And that's why although the energy and work done have same units, but when you compare them, what will happen is that energy will be equal to work done plus losses, right? Or you can also write as work done is equal to efficiency into energy. Efficiency of what? Efficiency of all these conversions. So there is a conversion between let's say DC to, so the DC energy is coming here, it is getting converted into alternating current here. So there is this conversion. This conversion will have some efficiency or inefficiency, I will call it now. And because of all these inefficiencies which are getting added up, this conversion is not true and there will be some losses. And to accommodate the losses, we are putting this efficiency term. Now, work done and energy will be equal if efficiency is 100%, right? So if efficiency of inverter is 100%, if efficiency of motor is 100%, transmission 100%, this all will have also wiring in it, right? Cabling. And because the current flows through the cable, there will be some heat loss, I square R loss. So if that is also zero, all the losses zero, all the conversion efficiency is 100%, then work done will be equal to energy. So in that case, you can equate the energy which is stored in the battery pack to the work done which is done by the wheel. And that's why we need to understand these terms. Okay. So from mechanical side, we need to understand how do I calculate work done. And from electrical side, I need to understand what is the energy which is utilized. And now I'll compare these two terms, work done in mechanical terms and energy which is stored in the battery in electrical form. If I compare these two, then I'll get to know the energy which will be required to get this much work done. So to go to this distance, let's say some Newton into meter distance, to go to this distance, how much energy is needed? Or with amount of energy which is available, how much distance can I cover? Same way, the force, how much force do I need to apply? Based on that, I'll be deriving the power, right? So that's what we are going to do in today's session. So to do that, again, let's understand what is the SI unit of power. What's SI unit of voltage? Current, energy. In electrical terms, SI unit of energy is, SI unit of power is Am I audible?
Yeah. Yes, sir. Please.
Yeah, so in electrical terms as well, the units will remain same. And that's why we are using SI units. Okay, because whether it is thermal unit, if it is on the mechanical side, if I'm using some thermal phenomena, I won't be using BTU. I'll be using the same joules to know energy. To know work done, I'll be using Newton meter only, which will be exactly equal to joules. Newton meter and joules are equal, right? 1 Newton meter is equal to 1 joules. Same way here, energy I'll be measuring in joules only. Power I'll be measuring in watts only. But I need to know what is the conversion of volt and ampere into joules or into watts, right? How do I do that? So let's take example of a battery again. So this electrical terms you are taking from battery, right? We talked about this. Battery is giving energy to the wheel. So battery's energy should be equal to the work done by the wheel. Battery's energy should be equal to the work done by the wheel. Now, to do that, I need to understand energy which is stored in the battery pack. And for that, okay, some slide I guess I might have skipped. So let me just check whether it is skipped means there it is there or not. Okay, I must have deleted that. Okay, so let's insert this new slide here. So what I want to do is I want to calculate energy of which is stored in battery pack. How do I do that? What I know about the battery pack, that its voltage I know, its capacity in AH capacity I will be knowing. Now can I convert voltage in volts and capacity in AH into joules? How do I do that? Okay, first of all, V into A, what it will give me? Voltage into current will be power. Power into time will be energy. Right? So V into AH is going to give me watt hour, which is the unit of energy. Power into time is energy. So watt hour is the time unit of energy. Watt hour, if I want to convert in watt second, what I will do? I'll have to multiply that by 3600, right? Because 1 hour is equal to 3600 seconds. So I'll get energy in watt second. Watt second, if I want to write in joules, how will I write? 1 watt second is equal to how many joules? 1 joules, right? 1 watt second is 1 joules, because this watt is also SI unit, second is also SI unit, so joules is SI unit. Now, the 1 watt second is equal to 1 joule. So if I have 100 volts battery with 40 Ah capacity of the battery, how many joules of energy will I have? 100 into 48 into 3600, right? So these many joules of energy I'll have. 100 into 48, 48 for 48 Ah, 100 for 100 volts. Ah to convert hours into second, and V into A will be watts, hours to second will be seconds, watt second will be joules. Yes, so 4800 into 3600 joules is our energy which is stored in the battery pack of 40 Ah capacity. Okay, I'll write it 4800, 4000. 4000, that means 4000 into 3600 joules, right? So how much does that become? How many zeros?
550.
Yes. So how many kilojoules or how many megajoules? 14.4 megajoules, right? So this is the amount of energy this battery will have. Now what is remaining is how do I calculate the or let's create a new slide. What is remaining is how do I calculate the energy which is required or work which is being done. To find the work done by motor, what will I do? What is the formula will I use? Torque into speed, right? Speed in which form? Rotational speed omega. Torque means tau. Tau omega we must have studied in books. Tau omega is the power up by the motor. But to calculate that, I need to find out what is the torque. To do that, I need to know what is the shaft diameter and then what is the wheel speed. So to not go into this, I can also convert the same thing into as a force into velocity, right? So this is in the rotational frame and this is in the translational frame. In translational frame of reference, force into velocity will give me what it will give me? Power. Power into time will give me energy. Or force into distance will give me energy. Right? And this distance is what? Range of the vehicle. This force is what? Force which is required for accelerating the vehicle. Force for acceleration, how do I calculate that? Mass into acceleration, right? So if I want my vehicle to move at particular acceleration and cover some 100-meter distance, then I can use this formula, force into displacement or distance or range. To calculate force, I'll be using ma. And then acceleration, I can find out from how much acceleration do I need. And then I can find out what is the work done by the motor, right? So this is a very basic thing which we need to understand, which I guess everyone knows, just I'm just repeating it so that we are getting reminded of it. So we can use it easily, okay? So now that the calculations we understood, let's take a look at some other things. So firstly, what are the inefficiencies which we might encounter? Let's assume that the vehicle is being charged through EV charger. And if charger is giving 100 units of energy, 1% of energy is lost in as a charger losses, charging loss itself. 0.5, okay, we'll take about recuperation later on. Recuperation is also termed as regeneration. We already have talked about regeneration. So regeneration and recuperation are both the same things. Now 1% is gone as charging loss, 2% as discharging loss. The battery will have some 98.5% inefficiency or 1.5% inefficiency, 98.5% efficiency. Now, if 100 is coming in, out of that 1% is gone, means only 99 came into the battery pack. Out of that 99, if I consider that 99 is 100, then 1.5 goes as a inefficiency in the battery pack itself. Out of this, let's say if this 98.5 comes out of that 2% will be lost in discharge losses, okay? So what is happening is all these inefficiencies are getting added up, or maybe we can just multiply them together. Firstly, the battery charging 99%, 98.5 as the battery's own efficiency. Discharge loss 2% means again discharge inefficiency of 2%, discharge efficiency of 98%. Auxiliary consumers asking for 6% of energy means only 94 is used for powertrain. Out of this 94, again 18% is loss in the powertrain itself. So loss in the powertrain is which is happening here. Where is it happening? It is happening in the inverter, it is happening in the motor, it is happening in the transmission, right? So all these losses put together, it is 18%. Just assume that 18%. So how much is actually going in? 82% is going in. Out of this 82, again, some of it will be used for overcoming rolling friction. When the vehicle is rolling, at that point, some of it is being used for lowering friction. So 23% of energy is lost in rolling friction, overcoming rolling friction only. So how much is remaining now? 77. Out of the energy which is coming here till this point, if I just multiply all these terms together, let's say if it is 70%, 77 of this 70% will be passed to the wheel. And out of this, again, some of it is also used to overcome the air drag resistance. It is 28%. So how much is actually utilized? 72%. Then there is some more for gradient loss as well. If I'm going uphill, there will be also gradient resistance which I need to overcome. Let's not consider that at the moment. So because of the gradient as well, there will be some losses again. And then remaining amount. So how much is that? Can you just calculate this? How much this number becomes? .99, or I'll just use 0.99. 0.99 into 0.985 into 0.98 into 0.94 into 0.82 into 0.77 into 0.72, and then this is the remaining amount. So the 60% of it is already gone in just overcoming the losses. Only 40% is coming, which is this 40% is used for acceleration m into a. Okay, so 40% of energy which is coming from the battery pack will be used for acceleration. Fine. And then your kinetic energy, which is half mv square, will increase because velocity is increasing. Now at this moment, if you apply brakes, and if these brakes are regenerative brakes, recuperation wala brakes, then again some part of it will be lost in 9% in rolling friction, 9% in air drag, 5% in braking loss, braking which is mechanical braking, frictional braking. So there will be also losses. Then losses in powertrain, because we saw that motor will work as generator, inverter will work as rectifier, so there will be some losses in it. Then auxiliary consumer. So while all these things are happening, your tail lamp, headlamp, brake lamp, infotainment system, fans, AC, all these things are also running. So they will also gain energy from this regeneration, and that we are just considering 4%. Let's say that AC is not running, and then remaining amount is put to the battery pack as regeneration energy. So this is how all the inefficiencies we are tracking. I hope you have understood where all the energy goes from one single battery pack. And now I guess we can just talk about what happens at this wheel stuff. So at the wheel stuff, what happens? There is some amount of energy which is lost in rolling friction, air drag. How much is lost? In rolling resistance, mu r mg. Coefficient of rolling resistance is mu r. Mg is m is mass, g is gravitational acceleration. Mg actually is normal force, right? N, Fn or N, which is called normal force into coefficient of friction will give me what is the frictional resistance. The values which are used for this mu r are shown here. And the generally used value for car tires is 0.012 or 0.02 based on what is the road condition and what is the tire material and so on. For steel rolls and steel rails and steel wheels, it is 0.001, very small. That's why railways use steel materials wheels and steel material rails, because that way they can increase the efficiency of the vehicle. The harder the wheel, the harder the road, lesser is the loss of the rolling friction. Okay, so I hope you have understood this. Let's move on to aerodynamic resistance, rho by 2 CD F V square. So you can just calculate what is the drag force from this. For this, let's look at how the CD value changes. CD is coefficient of drag. Rho is air density. AF is frontal area. V is velocity of the vehicle. Actually, it is a relative velocity with respect to wind. AF is also projected frontal area. Frontal area doesn't mean this area we need to consider. We need to consider whole area of the truck. So if I take the front view, it will look something like this. This is the front grille. Then this is the front body. There are these lamps, front lamps. Then these tires, the projected view of the tires. Then the compartment, driver compartment. This is the back portion of the truck. And then, so the area which we are interested in for AF is whole this sill out area, it is called sill out area. Okay. So if I take this out, it will look something like this. So this sill out area I am interested in. Okay. And not the only front grill area. Fine. AF means this sill out area, front view area. The value of CD changes based on shape of the object. So if shape is more streamlined body, so streamlined car will have lesser air resistance. That's why you see them running faster on the roads. The more blunt the car is, more drag resistance it has, more CD value it has. So the blunter shapes like cube has 1.05 value of CD. Short cylinder has 1.15. Then streamlined body has 0.04. So streamlined body 0.04. Half streamlined body, just like cars, 0.09. If you talk about cars, different cars have different drag resistance value. I'll just tell you some examples here. So Tesla cars have drag resistance value ranging from 0.23 to 0.26, I guess. And our Indian Mahindra cars, Tata cars, they have somewhere close to 0.3 to 0.45 like drag values, CD values. Generally 0.35 is what is observed in cars like Mahindra KUV, and for passenger cars in the sedan segment, this value goes little bit low, 0.3 or 0.32 like that. Okay, so I hope you have understood. Acceleration force, we already have talked about this, and then gradient is mg sine theta based on what is the gradient value, theta value gradient. So this much force with which the vehicle is being dragged towards the ground, Fg will be mg into sine theta. So without wasting much time, let's try to solve this one particular numerical. And to solve this, you'll need formulae. All of the formulae which are required to solve this are listed in this slide. Okay, somehow it is not working. So these are all the formula which are clubbed together. And this is the numerical. Let's solve this. I'll give you 2 minutes to solve this. If not, I'll solve it myself. So has anybody been able to solve it?
Durvankur Raut, sir, we can continue, I think. We can
Okay.
continue.
Okay. So we just have a few minutes left. Let's try to solve it ourselves here. Okay, I cannot solve it in this. Okay, what does the problem says? That the vehicle is cruising at 40 kmph. What does cruising mean? Cruising means that it is not accelerating and not decelerating. It is at constant speed. So if it is at constant speed, what is the value of acceleration? A? 0. So we'll just take the inputs as A is equal to 0. What else is given? Speed is given 40 kmph. So V is given 40 kmph. We need to convert this into SI unit. We saw that everything needs to be in SI unit. So just multiply it by 5 by 18. And what value do we have?
11.11
meter per second.
11.
Right?
Yeah.
So velocity is 11.11 meter per second. Battery pack capacity is given as 100 Ah 48 volt. So we'll be calculating energy of battery pack as 100 into 48 into 3600 volt, right? We saw that earlier in one of the slides. 4800 into 30. Vehicle is in rectangular brick shape with height given as 2 meters. Yes, can you please keep on mute, sir? Yeah, height given as 2 meters, width given as 1.5, length as 5 meters. So frontal projected area will be height into width, which will be 3 meters square, right? 2 into 1.5. So AF is 3 meter square. Length, we don't bother about length because it doesn't come in any of the formula. Gross vehicle weight of the loaded vehicle is 1 ton. So we'll be just considering that as mass of the vehicle as 1000 kg. Use following values. Drag coefficient CD value is given 0.35. What else is given? Rolling coefficient of friction 0.02.
Mu R.
0.02.
Rho is given.
Quantity of air as 1.2. So rho is 1.2. What? 1.2 what? Kg per meter cube.
Meter cube.
Right? Does the CD and mu R have any units? No, they are unitless quantities, ratios. So they are unitless quantities. What are other values we'll be needing? Value of G, which is gravitational acceleration 9.81 meter per second square. So these are the numbers which we already know. Now we know what is the energy, 4800 into 3600. Let's calculate work done. To find out work done, we know that it is force into displacement, yes. And yes is the range which is asked, which is unknown. What is been asked? Calculate range and max power requirement. Range will be distance in force into distance wala. And max power we can calculate based on force into velocity. Velocity is already known, force is something which is unknown. Force we need to calculate now. So to calculate force, what I'll do? I'll have to see how much force is used by the vehicle to cruise at 40 kmph. So to cruise at 40 kmph, what are the other things which are happening as it is cruising? Is there any acceleration which is happening? No. So acceleration resistance will be 0. Is there any gradient which we are encountering? No, because it is a flat highway, it says. So gradient also, theta is 0, so Fg will also be 0. Now, what other two resistances I need to overcome? So if I need to keep at constant speed, I need to overcome this rolling resistance and drag. So I'll just calculate these two forces, add them together, and I'll have value of what is the total force I need to apply on the wheels so that the vehicle remains in the state of motion, which is constant speed. Okay, if I don't apply any force, then because of these negative forces, so the aerodynamic resistance is also pushing the vehicle backwards, inertia is pushing the vehicle backwards, internal friction, gravity, all of them are pushing the vehicle backwards. If you want to stay in the same velocity, you need to apply exactly same force as that of the addition of all these forces, in this case these two forces, so that the vehicle remains in the same speed. Now to calculate these two forces, what we will do, we'll just use the numbers which were given in earlier slide. Mu r was how much? 0.02.
0.02. Mass is 1000. And G we should take 9.81. Okay.
Yeah. So total value becomes how much?
Almost 1.
Right?
1 minute, sir. Yeah. It's 196.2 FR.
And this is
7.
70.
7, only 7, I think. Yeah, 7.
No. You have forgotten to add v square then.
Oh, B is correct. Yeah.
77.77, right?
Yes, 77.7. Correct.
Now just add these two values together. What value do you get? 273.97.
Yes.
Right? Newton as the total force. So let's go back to this slide again. The force is 273.97, or we can just call it 274 Newton. So 274 Newton into some displacement x is equal to 4800 into 3600. You just now check the unit systems. Is everything in the SI unit system 274 Newton? It is in SI. Then it is in joules. This energy is in joules. So we can just exchange these values and we can find out what is the value of x. Okay, sorry, we have taken s as the distance here. Let's use the same one. S. So 4800 into 3600 divided by 274.
$63,065.
Okay. And what will be unit of that?
It will be meter, no? Meter.
So this is in meters. If I want to convert this in kilometers, I will be dividing by 1000, which becomes 63.06 kilometers. Now let's take a look at that numerical again. The answer which we have is 63.07 kilometer. We have received. Now let's calculate power. Power is how much? Force into velocity. Force is 274 velocity is 11.11, so it comes down to 3000 something. How much? Are you getting 3000 as answer?
Yes, sir. Yes.
3050, let's say, which is 3.05 kilowatt. So that's how you can calculate what is the motor size and what is the battery pack size. So for sizing the motor, this value will be used. For sizing the battery pack, if battery pack size is known, this is how you can calculate the distance. Where is that distance? And if the distance is known, the same way you can back calculate the energy, which will give you battery pack size. But what are the things which we did not consider? Firstly, all the efficiencies we did not consider, right? If we consider all the efficiencies, then the numbers will be different. We did not consider that the vehicle does not always move at the same constant speed. It might accelerate. So if I draw velocity graph versus time, it might accelerate sometimes, it might remain at the constant speed, might accelerate again, might remain at constant speed, might drop down the speed to zero back again. So this is how the velocity changes. And when what we just solved right now is this portion only. What happens when the vehicle is accelerating? At that point, FA value will be non-zero. When the vehicle is accelerating, FA value will be non-zero. Sorry. And when the vehicle is going uphill, gradient resistance value will also be non-zero, right? So these values, if we consider, then you can also calculate what is the battery pack capacity or motor power based on the inputs which we are giving here. Now, with this, because of the time constraints, we can conclude here, I would say. If you have any questions, I can take them right away.
Thank you, sir. Thank you very much. So participants, you can post your questions in the chat box, or you can unmute your mic and you can directly talk to the resource person.
Sir, I have one question. Sir, we have calculated the battery power in the last question, 3.05 kW. This is the minimum requirement for.
That is not battery power, it is motor power.
So this is sorry, motor power. Battery power we can calculate from the range, no?
Yes. Now the battery energy was already given as input 100 ampere hour and 48 volt, which is equivalent to 4.8 kilowatt hour. 48 into 100, 4800 watt hour, which is 4.8 kilowatt hour.
Okay, but you told this is only for the constant velocity. But if we have to consider for the acceleration and this gradient also, then that motor, that capacity will, I think it will increase.
Yes.
It should increase, no?
Yeah, it should. So if I am drawing, let's say, just give me a moment. If I want to draw how the motor power will vary on this same graph, it will look something like this. I hope you'll be able to see the green color. Is this green color visible?
Yes.
So in that case, this is how motor power will rise, and this will rise with second order curve. At this point, it will suddenly drop down and it will remain constant throughout. Again, as this is accelerating, this will rise up. Again, it will drop down, constant till this point. And as it is decelerating, this will drop down further like this, and it will come to 0 like this. So this is a motor power graph will look like. So if I draw it separately, now these values, of the peaks, that will depend on what numbers we are using. So this is how the motor's power graph will look like. Now, if you are selecting a motor, this value we have calculated right now as 3.05 kilowatt. But when you are accelerating, this number is going to be higher. And this higher number will based on how fast do you accelerate. If you want to accelerate faster, means within a lesser number of time, with lesser amount of time, then this number will rise further. Okay. Same way, if you apply brakes faster, then this line will go down further. More amount of power needs to be taken out from the vehicle. Okay, I hope you have understood.
Yes, sir. Sir, can the use of gearbox can reduce the motor power?
Power, it won't reduce. The torque, it will reduce or increase.
Capacity of the motor.
Motor torque is adjusted by means of transmission, so not the power. Monish, can you tell me a brief about yourself? Where are you working?
I'm working in MIT Academy of Engineering, Alandi, Pune, and I'm doing research in this gearbox, EV gearbox.
Okay, okay. So you seem to know a little bit more about vehicles. We can talk about it maybe separately again. So
yes, sir. Surely. You are from Pune only, so I will contact you, sir. Surely, I'll contact you.
So this is the name of the company currently we have recently launched. It is in the field of automotive, especially on the EVs. If anybody needs any lab equipments, especially for colleges, we can provide so through AMI Labs Private Limited. This is a new company which I have launched. You can reach out to the company phone number if you are interested, or this is my personal phone number.
Yes, sir. Surely. I'll contact you for that. Yes.
Yeah. Okay, so we can call it an end, right?
Okay, sir. Thank you, Monish, sir. And I think no more queries from the participants. So if there are no queries, I will wind up now. So it was a very wonderful session, very informative and interactive session too. The resource person has made the session very live by solving the numericals, and also has given a very detailed information about the electric vehicle architecture and all the calculations involved in the calculation, in finding out the various power parameters. So thank you, sir. It was a very good session. So on behalf of the management and Department of Mechanical Engineering, I express my heartfelt gratitude to Mr. Durvankur Raut. In spite of his busy schedule, he has made some time to share the knowledge with us and enrich our knowledge. So thank you very much, sir. Thank you for being a part of this FDP. So thank you very much.
Yes, thank you very much, everyone. Have a good day.
Yes.
We have one more session, right, to go.
Yes,
maybe
yes,
day
yes,
after tomorrow or tomorrow itself. So see you then, and you can reach out to me for any queries. Thanks a lot.
Yes, thank you very much, sir. And also, I would like to thank all the participants who are actively participated in the session. So now let us break for the lunch, and we'll again assemble back at 2 p.m. for the third session of this day. So thank you everyone. Thank you very much.